Today we're going to be looking at a couple of theorems that come as consequences of a function being continuous. The first theorem that we're going to look at is the extreme value theorem. It states that if f is continuous on a closed interval from a to b, I can find x values of little m and big M in that same interval such that f of little m is the minimum value of the function f of x on the interval from a to b, and f of capital M is the maximum value of your function on this interval. Let's look at the graph of a function to kind of illustrate this theorem. So we can see this function here is continuous on the interval from 3 to 6. So what the theorem says is that I can find an x value, probably right around here, that we call little m, such that f of m is the minimum value for my function on this interval. So that means that my function is always above f of m, which we can see. And then we can also, because this function is continuous, find a capital M such that f of capital M is my maximum value for my function. So my function is always below this line right here. Now note that this theorem doesn't tell me what these values of little m and big M are, it just says that they exist. When we get into studying derivatives, we'll find a little bit more about how to find the actual values of little m and big M. Now I want to point out a couple of examples of why this idea of continuity is so important in this theorem, that we have to have my function continuous to begin with. So let's look at the function here that looks like this and has an asymptote in the middle, so we have an infinite discontinuity. So this is not continuous because of that discontinuity, and we can see that this has no minimum value because my function just keeps going off to negative infinity. So we have to have continuity in this definition in order for the conclusions of this theorem to work. We also have to make sure that my function is closed on this interval. If not, I could have something like this, which again has no minimum value because my function will never actually reach that point right here. But as long as my function is continuous on a closed interval, I can conclude that the minimum and maximum values are attained by some little m and big M in your interval from a to b. Let's see how the extreme value theorem applies to this example. I'm given a function w of t that represents a person's weight at any time t, measured in years. So first we want to show why this function is continuous on the interval from 18 to 22. So this function again would represent this person's weight at any time between 18 and 22 years old. Let's imagine what the graph of this function would look like. So at 18 years old, you have some weight, and then from then on you might gain some weight, you might lose some weight, but there won't be any places where your weight suddenly doesn't exist, like a removable discontinuity. Your weight isn't going to go off to infinity with an infinite discontinuity. And you can't have any kind of jumps in weight. If you ever gain or lose weight, there will be some amount of time in which it happens rather than it being a sudden jump. It can't be instantaneous. So between 18 and 22 years, your weight is going to be nice and continuous. So because my function is continuous on a closed interval from 18 to 22, I can use the extreme value theorem to make the following conclusions. First, we can say that there exists some time t sub little m between 18 and 22, such that at that time this person weighed the least amount that they ever weighed between 18 and 22 years old. We could also make the same conclusion about the maximum weight, that there is some point in time between 18 and 22 that they weighed their most. Again, this theorem doesn't tell me what those times are, it just tells me that they exist. Now let's look at the intermediate value theorem. It states that if f is continuous on a closed interval from a to b, then for any value k strictly between f of a and f of b, there exists some value c in the interval from a to b such that f of c equals k. So again we have this graph of this function that is continuous from a to b, and now I'm going to add in that I look at the values f of a and f of b. What this theorem says, if I pick any value k between f of a and f of b, so let's say here, then I can find a corresponding c in the x interval such that f of c equals k. Again, the condition that the function be continuous is necessary in this theorem, because if I looked at this function here from a to b, that maybe has some kind of a jump discontinuity. So here's f of a, and here's f of b, but now I can find a value of k such that there is no x value c such that f of c equals k. Your function kind of jumps over that y value. So what the intermediate value theorem is saying, that if your function is continuous, then your function will hit every single y value between f of a and f of b. Let's again look at the weight function with the added condition this time that at 18 years old this person weighed 130 pounds, and at 22 years old they weighed 185 pounds. So my function goes something like this in a continuous manner from 18 to 22. So what the intermediate value theorem says is that any weight between 130 and 185 pounds, at some point in time you weighed that much. So if I look at 150 pounds, there's some point in time where you weighed exactly 150 pounds. Or I could do this for 180 or 131, or any value of weight between 130 and 185 pounds, at some point you weighed that much. Again, this theorem doesn't tell me what these values of time are. It just tells me they exist. So let's say instead my function looks something like this. So now if I look at that value of 150 pounds, I might have multiple times where I weighed that amount, that exact amount. But this theorem guarantees that there's at least one time that that happens. The intermediate value theorem is also helpful in showing that a function has roots or x-intercepts on some interval. So let's look at the function f of x equals x cubed minus 3x plus 1. Now this is a function that we can't factor as easily, so finding the exact roots might be difficult, but I can at least use the intermediate value theorem to show that these roots exist. To use the intermediate value theorem, I first need to check that f is in fact continuous on the closed interval from, in this case, 0 to 1. But this is true because f is a polynomial, which are continuous everywhere. So it's definitely continuous on the closed interval from 0 to 1. Now I need to check the value of my function at both of the endpoints. So if I plug in f of 0, I end up with 1. And if I do f of 1, I end up with negative 1. Since one of these values is positive and one of them is negative, that means between them is the value k equals 0. And now I can use the intermediate value theorem to say that there is some c in the interval from 0 to 1 such that f of c equals 0. So this c would be the root that I'm talking about here, that's somewhere between 0 and 1. I don't know the exact value of it, but I know that 1 exists by the intermediate value theorem. Now let's see what happens on this function on the interval from 1/2 to 1. So we already found that f of 1 equaled negative 1, and then you can calculate that f of 1/2 equals negative 3/8. Because these are both negative, 0 isn't between negative 1 and negative 3/8. I can't use the intermediate value theorem to guarantee that there's an x value of c such that f of c equals 0. I can only do that when my y values you have one positive and one negative. Now, a root might exist between 1/2 and 1. I just can't use this theorem in order to guarantee that a root exists because the hypotheses of the theorem aren't met, so I can't make any conclusions for sure. So when my function is continuous on a closed interval, I have the extreme value theorem and the intermediate value theorem from which I can gather more information about the functions.